Right, I'll make a start. I was going to wait a little longer. My tea is too hot to drink right now, so I'll drink it throughout the 3-minute silence. As usual, and we now have, I think, 10 in the room. Really, really nice to, as it were, see you all again. Thank you once again for tuning in. Back down to 9, already lost one. But as always, just let me know you can hear me just by at least one of you replying. But assuming that you can, we'll start in the usual manner. I will put up today's lesson title. And today we're learning about something called the generator effect. And that's today's title. It's a little small to see. Yep, you can hear me. Lovely. Thank you for the confirmation. The title is the generator effect. As always, I'd like you to do the usual jobs. So please can you put your title in your book, update the contents, and have a read over at the very least, and perhaps even do a written question about last time. I'm going to start again with one of my quizzes. So the last thing I need to say before I start my timer is you might want a scrap of paper ready, because some of you might not want the quiz to actually go in your book. That's up to you. But we'll do 3-minute silence, do the usual jobs, get a piece of paper ready for a quiz if you want, and then we'll make a start. Thank you very much, everyone. 10 minutes. 3 minutes, sorry, 3 minutes. Two more minutes. Welcome if you just joined. We're up to 11 people currently in the room. If you didn't hear what I said before, we're just in our usual 3 minutes of silence. And I also said, just get a piece of paper ready, because we're going to start with a quiz. And some people prefer not to have that in their notes. You've got 1 more minute, just over. Right, super. That's the 3 minutes done, and hopefully, as usual, that was enough time to get yourself ready for today's lesson. So this can be on a scrap of paper if you prefer, but I'm going to do possibly a 10-mark quiz. I'm going to split it into 5s. So these first 5 questions are actually from anywhere within the physics course, and then the last 5 will be more recent. But I will go through the first 5 before going to that second quiz, just in case it all takes too long. So As always, I'll try and judge the timing of this, but I'm going to ask a question, give you a moment to answer, then move on to the next one. We'll do 5 questions, go through them, and then we'll move on to another 5 questions if it feels like it's not dragged too much. Last thing to say, as always, is sort of don't cheat it. So just make sure there's nothing in front of you. I just want you to see what you already have in your head and see what gaps may have appeared. So the first question is from the radioactivity topic, and it's one for you to draw. Could you draw a picture of a chain reaction, please? Draw a picture of a chain reaction, and I'll give you a short amount of time. I won't time it, but I'll just give you a moment to just sketch out a picture of a chain reaction. Give you about 10 more seconds, I think. So that was question 1, to draw a picture of a chain reaction. Question 2 is a complete the sentence, and there's really only one answer that will suffice here, and let's see if you know it. When a spring is stretched and can then return to its original length, it is known as. So when a spring is stretched and it can return to its original length, it is known as what? That's certainly enough time to write the answer if you know it. So here's question 3. And actually this is a contrasting question in that this is quite an open one. That last one probably really only had one answer. This has a few potential answers. Try and list 2. I'd like you to try and list 2 factors which affect reaction time. So particularly in the context of cars and driving, 2 factors please that affect reaction time. I'll give you a moment to write 2 factors. So that was question 3, 2 factors that affect reaction time. Question 4 feels open-ended. It's not really. It has an answer, and I think you'll either know it or not. It's just one of those, really. The question is this: what surrounds a charged object? What surrounds a charged object? That's question 4. So question 4, what surrounds a charged object, and then question 5, the last one we'll go through for now so that we can review them. Physical changes are ones which can be something. So now complete the sentence. Physical changes are ones which can be something. And I think with 2 or 3 of those, actually, it was a sense of either you'll remember it or not. It's perhaps less guessable. We'll see. We'll see. And we'll go straight through them now. So clearly no need to change colour of pen unless you want to, unless you have the pens to hand. You're just reviewing this for yourself. And I think to speed things along, I'll just give answers rather than asking you to supply them. Not least because I'm not quite sure who's with me. There's 11 people watching. Thank you very much for tuning in. Just not sure who those 11 are. So we'll go through them, just me giving the answer. Diagram of a chain reaction was question 1. And there's a few features that a diagram of a chain reaction should have. So I'm just trying to hold this board in about the right place. Well, a chain reaction is something that happens to the nuclei of atoms. So your diagram certainly has to have some nuclei. But the whole point of a chain reaction is what happens after they split and some neutrons get released. So this first nucleus absorbs a neutron. So I'm just going to label N for neutron there. That nucleus absorbs a neutron. It becomes unstable and it splits. We're in the world of nuclear fission here. So the next thing in your diagram might show these two sort of halves of that original nucleus. But that's not the chain reaction, that's nuclear fission. The chain reaction comes from the loose neutrons that also get scattered off. So your diagram should have perhaps 2 or 3 neutrons that have scattered off from that original split nucleus. And then to properly show a chain reaction, you then have to show how they themselves will get absorbed by another nucleus. So up here, somewhere in this direction, another nucleus waiting to absorb that neutron. Now, your diagram is certainly not going to match mine, but it has to have the same essence to it, I suppose. And to show that it's a chain reaction, I suppose I've also got to show that these neutrons, sorry, I'm off screen, that these neutrons, it's really hard to coordinate, there we go. These neutrons go on to induce further nuclear fission, so you could show that these all get split up. And the thing about a chain reaction is it has no obvious end, so with diagrams it's sometimes hard to know where the obvious ending is. But once I've drawn it, I'll just show you what I've got. Getting messier as I go. But that is somehow, there we go, sorry, in screen there. That's roughly a picture of a chain reaction. This idea that that one nucleus gets absorbed by, that one neutron gets absorbed by that one nucleus. That nucleus splits, it releases 3 neutrons, and those 3 neutrons then go on to induce further fission here, here, and here. That's how you draw a chain reaction. Question 2, anyway, was a much more closed question, really. And it went like this, sorry, just retrieving a pen lid. Question 2 is to complete the sentence. When a spring is stretched and can then return to its original shape, it is known as, and here's the answer, elastic deformation. More broadly, you could call it elastic behavior, that would be fine, but elastic deformation is what I was looking for. Question 3, factors which affect or influence reaction time are. Now this might not be an exhaustive list, but I've got 4 written down here. Things like tiredness affect reaction time. Being under the influence of intoxicants, so that could be drugs or it could be alcohol. Distractions, and we also mentioned in lessons the effect that age can have as well. All of those things can affect reaction time. And I asked for any 2 of those, 4 or 5. Question 4 was what surrounds a charged object? And the answer to that question is an electric field. And just to draw that really, really quickly, it kind of brings us back around to thinking about our magnetic fields, but around a charged object, in this case a positively charged object, there is a radial field going off out in all directions. Technically that field goes on forever, weakening as it goes out. And field diagrams always need arrows. In this case, you always define it as being from the positive towards negative. So in this case, you draw a field, something like that. But the answer to the question was an electric field, is what surrounds a charged object. And then question 5, physical changes are ones which can be reversed. The answer to that one, reverse, question 5. I will, because it's useful now to go through some stuff that's more recent, do a second quick quiz, again out of 5. So be ready with a piece of paper again. And the first of this second quiz, the first question is, I'd like you to write the definition, keep it as brief as you can, of a magnetic field. What is the definition of a magnetic field? Question 1 of this second little quiz. That was question 1 of this quiz. What is the definition of a magnetic field? May have judged that badly, but I'm going to move on to question 2. What is the unit of magnetic flux density? And I could also describe that as magnetic field strength, but I want the unit of that quantity. What is the unit of magnetic flux density or magnetic field strength? What type of magnet loses its magnetism? It is removed from the field. Just noted some connection problems popped up on my screen. There may have been a brief pause there, but there's nothing now saying there's a problem, so I'm going to assume everything's fine. Question 4. The strength of a magnetic field surrounding a conducting wire depends on. So if you've got a current carrying wire, it has a magnetic field. What does the strength of that field depend upon? That was question 4. And then question 5, I'm looking for 3 answers. I'd like you to give 3 ways of increasing the force on a current carrying wire in a magnetic field. So when you take this current carrying wire and you place it in a field, it will experience a force. Give me 3 things that influence or increase that force. And we'll go through those. I want to be fairly sort of snappy with what I do here. I hope I've given you about the right amount of time. So question 1 of that second quiz, and this was all this most recent topic. What's the definition of a magnetic field? Well, clearly this isn't going to be word for word, but just check it against yours. It's this idea that a field is the region around a magnet where another magnetic material will experience a force. The region around a magnet where another magnetic material will experience a force. Question 2 was about the units of magnetic flux density. Well, it's measured in Tesla, capital T, or the word Tesla. Question 3, what type of magnet loses its magnetism when it's removed from a magnetic field? What's being described there is an induced magnet. An induced magnet loses its magnetism when it's removed from a magnetic field. And question 4, the strength of the magnetic field surrounding a current carrying wire depends on. Well, the main thing it depends on is the current that's running through that wire. Best answer there, the current. You might have mentioned the distance away from the wire, but the current determines the overall strength of that field. Then question 5 was about give 3 ways of increasing the force on a current carrying wire in a magnetic field. And I think the best way to approach it is to remember an equation. F equals Bill. There are your 3 things. If you want to increase the force on the current carrying wire, you can increase the strength of the magnetic field. That's B. You can increase the current. That's I. Or you can increase the length of wire that's within the field, often by coiling it up. But the length of wire in the field is the 3rd thing you can increase. Conceivably, there might be another answer there, but I think they're the best 3, and they come straight from the physics of the system. Well, again, you can give yourself a mark out of 5, but now we're going to move on with some new things. And what we're looking at today is something called the generator effect. So I think without further ado, I'm going to move the camera around and show you a demonstration of the generator effect. So bear with me a moment as I move my camera. The mug of tea is not part of this, I will move it in a minute. Before I show you that though, actually, and bear with me with a slightly wobbly handheld experience with the camera, I just want to show you something I've got on my screen. This is our story so far. It's the motor effect. And remember, with the motor effect, what you put in is electricity. You have to have a source of electricity and a magnetic field. Magnetic field here. If you put those two things in, then what you get out is movement, and we call that the motor effect. When a current carrying wire is in a magnetic field, it will experience a force, the motor effect. So you put in the electricity, you put in the magnetism, and out of it you get movement. Well, to Michael Faraday, who discovered the motor effect, that begged an obvious question. It begged the question, well, if you can put in those two things and get out movement, what if you put movement into magnetism? Can you get out electricity? And the answer is that you can, and I'm going to show you that now. So what I've got here, I'll just explain what I have. This is a voltmeter, but it's no ordinary voltmeter. I'm just pressing a button called auto zero, and you'll see the needle go to the 0 line in the middle. Just takes a moment to creep into the middle. But that there is a voltmeter, but as I say, it's no ordinary voltmeter. It's actually called a micro voltmeter. And you can see the word there, micro voltmeter. In other words, the voltages I'm about to measure are really quite small, and a normal voltmeter just isn't sensitive enough to show it. Bear one thing in mind, even though this is plugged in, even though it looks like a power pack, it's not supplying any power to the circuit. It is simply measuring what voltage there is. And once again, it's a bit of a stretch to call what I've got here a circuit. It's not much of a circuit. It's a loop of wire. There is nothing else playing any part in this circuit. There's a loop of wire. The circuit connects to a voltmeter here, and that's it. And so on the face of it, there is nothing to make voltage. And yet, and you will only see it a small bit, watch for small deflections on that needle. And in fact, I'll move everything in now as close as I can. And I'm going to hold up the wire so you can see what I'm doing. I'm just going to bring a magnet close to it. And if you pay really good attention, and I think the quality is good enough on my screen for you to see it, if you pay really good attention, you'll see there is a tiny, tiny deflection on the wire. The smallest deflection, but it's there. Watch what happens now as I do a few different things. So the first thing I'm going to do is this red side that you can just see, this red side of the magnet. I'm going to approach the wire with it and then stop moving and look for the direction of the deflection. It deflected slightly to the right. Now I'm going to pull that north away. Much harder to see, I could see that, but it deflected slightly to the left. I'll do that one again. So as I pull it away, it deflects ever so slightly to the left. Now when the south approaches it, we should see it deflect again in a certain direction. So remember, when the north approached, it deflected to the right. Now when the south approaches it, it deflects hopefully to the left. A bit more convincing there, the initial deflection there to the left. And then it makes sense that if you pull the south away, instead of deflecting to the left, it should deflect to the right. But again, it will be a minimal deflection you're seeing there. Bit clearer that time. So we're learning something about what happens. What we're learning is that actually, when this current carrying wire experiences a magnetic field, a current will be induced. The word is induced. There'll be an electric current. It's like there's a battery there, but there isn't. There is nothing that we would think of as a power source to create that current flow, and yet there is a current flow. It's called the generator effect. When a current carrying wire experiences a magnetic field, it will create an electric current. And perhaps this is no surprise to you now, but what you can actually do to increase that effect is just make a bit of a homemade solenoid. All I'm going to do is coil this round a few times. So now I've got a coil of wire. It's clear enough on the screen. I should have gone with the red wire. It would have stood out much more clearly. That's a coil of wire, and what I'm going to do now, look for the deflection now when I move this through. Much bigger deflections possible. That's the generator effect. All I've got is a piece of wire and a magnet, and I am making electricity out of it. So not only did Michael Faraday give us the motor, which is the basis of so many of our wire moves too. I can keep the magnet still and move the wire instead. As long as there's relative movement between the two of these, as long as this piece of wire experiences a changing magnetic field, it will induce an electric current, and it's called the generator effect. So that's not the only thing I'm teaching you today, but we will capture some notes around that. And I just want to show you quickly on the screen what you've just seen, perhaps in a clearer sense. It's known sometimes as Faraday's law of induction, as you can see there. But you have this idea that if you move a magnet relative to a current carrying wire, and it doesn't matter which of the two you move, it will generate a voltage. And you can see that actually the direction of that voltage depends on which way the magnet is moving. And we'll come to that a little bit later in the lesson as to how you know what direction the induced voltage will be created. But first we're going to make a simple note about the generator effect. You'll need a pen and a pencil, possibly a ruler as well. So just make sure you have all those three things to hand. Right. I'm hoping I've created something that's going to be clear enough to see. There's not a huge amount of note taking required, but we are going to punctuate it with some useful diagrams too. Just fetching a ruler from my supplies. I'll just be one moment. Right, sorry about that, everyone. Back in the room and about to make some notes. We don't need a subheading, I wouldn't say, because our heading was the generator effect. So we'll start with this. When a conductor and of course by conductor I mean electrical conductor, but I think from context that's clear enough. When a conductor experiences a changing magnetic field, comma. So when a conductor experiences a changing magnetic field, a potential difference is induced across it. Full stop. When a conductor experiences a changing magnetic field, a potential difference is induced across it. Well, I'm going to punctuate this little note with some diagrams of what I've just described. So in order to do that, we'll have something providing the magnetic field. In other words, a picture of a magnet. And next to it, a bit like we saw on our screens, something that to our eyes would look like a coil of wire. And the idea is this. Let's say we move that magnet. Well, that coil of wire, that solenoid, experiences a changing magnetic field. And when I say that a potential difference is induced, what I mean is that it ends up almost becoming a battery. So we're just going to put a V and a plus and a minus to show that a voltage is induced. Well, I've deliberately made this an unconnected circuit. So that happens whether it's in a complete circuit or not anyway, but on its own, perhaps not much use. But the idea is if this is now part of a bigger circuit, it can make a current flow in that circuit. So we're going to carry on by saying this. If the wire is part of a complete circuit, if the wire is part of a complete circuit, comma, a current will flow. Full stop. So this time I'm going to draw a very similar diagram to the one just above, but this time this wire is going to be part of a complete circuit, which means that a current will flow. So once again, I'm going to draw my magnet, no different to last time. Its movement no different to last time either. This time, this solenoid is going to be linked to a wider circuit. So I'll put an ammeter in there. And just to really emphasize the point, we'll put arrows to show there's now a direction of current traveling through it. And we'll put the words underneath, current flows. And to sum this note up, then one final sentence. This is the generator effect. This is the generator effect. So the previous lessons have dealt with the motor effect, where you get movement out. This deals with the generator effect, where you get electricity out. Just going to read through that and hope it does make some sense to you, seeing it all in context. When a conductor experiences a changing magnetic field, a potential difference is induced across it. That's what we're seeing in diagram 1. If you just have a piece of wire in a magnetic field that's changing, it will make a little voltage. Then we go on to say, if that wire is part of a complete circuit, a current will flow. So that voltage will produce, when it's allowed to, a current flow. And that idea that we can induce an electric current just by changing magnetic field near a conductor, it's known as the generator effect. Maybe just to tidy up that note, let's just list 2 or 3 things that can increase this effect. The effect is increased by, and the first thing we'll list is a stronger magnetic field. Stronger magnetic field. Now next, what we could say is faster movement, but there's a better way of saying faster movement. What the faster movement actually causes is a quicker rate of change of the field. So we're going to put greater rate of field change. And also, as you saw with me, we got a bigger effect when I added a coil of wire, when I just simply put more wire into the field. So the third thing we can list is greater length of wire, or greater length of conductor, to keep it general. Those three things all increase this effect that we see. Well, I've got one more thing to show you. Sadly, I've not got the equipment here at home to show it physically, but I'm going to show it on screen. One last thing we need to understand from this. I've not seen any other questions pop up, which presumably means there aren't any. That's fine. If you do, as always, if you do have any questions, just ask them of me. If I'm not making anything clear, do ask it, because it's unlikely you're the only one out of the 10 or 11 of us that is struggling to understand if that's the case. So I'm just going to move my camera around back to the original screen that I show things on. Nearly worked. And actually, for the purposes of this, less about me, more about the screen. So I'm also going to zoom into the screen. I think that should show things well. So you've seen this picture already. This picture is Faraday's law of induction, or what we're calling the generator effect. When a current carrying wire experiences a changing magnetic field, an electric current will be induced if that's part of a complete circuit. If not, it will induce a voltage, which could then lead to a current flow. But the other thing I want to show you is this. It's the second thing for you to understand. I'm just going to turn the light off my camera again. It's just slightly blinding me like last time. Second thing is this. Now, I don't have the facility to pause this image. So you pay good attention to what's happening. Something about the direction of the field that we need to understand. We are inducing a current here, and we're inducing this second thing to become a magnet. When this first magnet, the permanent magnet, approaches it, it creates a magnet with a north there, a south there. When it moves away, it's a south there and a north there. And just persuade yourself of that. Oh dear, sorry. Watch that really carefully. When the north approaches, this is a north. When the north moves away, it becomes a south. That's telling us something about how this behaves. What it's telling us is this. That the magnet you create here and the current you create here, look, that's changing too. They are created in a direction to oppose the change that created it. That's a mouthful, and it's one of the most, I think, sort of head-turning and difficult things I've tried to teach you in these online lessons. But the magnetic field that's created here is created in a direction that opposes the change that created it. If you go on to do A-level physics, you'll give this law a name. It's called Lenz's Law. We're not going to use that name here. I don't want to add too many words and too many names to what you have to remember. But at A-level, this would be called Lenz's Law. The field that is induced, the magnet that's induced, is created in a direction to oppose the change that created it. Let's see what that means here. It means when north approaches, this is a north. In other words, as the north approaches, it wants to push away the north, stop the change that created it. So as the north approaches, it becomes a north to try and undo the change that's creating it. Whereas when this moves away, it becomes a south. In other words, it wants to pull that magnet back. It wants to oppose the change that's created it. So the direction of field that's induced is always created in a direction to oppose the change that created it. We're going to make a note of that, but I think it's absolutely best shown through a diagram as well. So we're going to do it as a diagram as well. And I've not seen any questions. I'm just pausing again to see if there are questions. But I think this is one of the most difficult things to get your head around that I've taught you so far. So hopefully the notes will help solidify for it if you're a little bit confused by what I just said. So a bit of shuffling around. These are the last notes we're going to do. And then it's over to you to do some questions for me. So let me zoom out. And I'm going to move my camera around again. That's okay, and I'm going to turn the light on and adjust the focus. And a fresh sheet of paper required as well. This does, I think, suggest a subheading. And the subheading we're going to put is direction of induced field. And we're going to put field slash current, because one affects the other. So a note about the direction of the induced field or the induced current that is a result of it. Right. So in the generator effect, comma, the current induced in a conductor in the generator effect, comma, the current induced in a conductor is created in a direction to oppose the change that created it. In the generator effect, the current induced in a conductor is created in a direction to oppose the change that created it. I think that's much better understood through a diagram. And this is our last note, just two complementary diagrams that illustrate what we were just saying and seeing. So in the first one, again, we'll start with a magnet north, south, and we'll have our conductor. And in this first case, we've got a south approaching. We've got a south approaching that conductor. So the generator effect tells us that that's going to become an induced magnet and it's going to create a current flow. Well, because it's a south approaching, what will oppose that change is if this also becomes a south, and therefore this becomes a north. In other words, this induced magnet is opposing the change that created it. But it works both ways. So in this second diagram, we'll keep the magnet the same way around. But this time the magnet is moving that way to create a changing magnetic field. And so once again, we can draw our coil, we can draw our solenoid. But this time, because the changing magnetic field is being created by a south retreating away from it, the thing that would oppose that change is if it becomes a north. Then it wants to attract it back. It wants to undo the change that's creating it. And so you end up with north-south as opposed to south-north. So I hope those two diagrams slightly solidify the idea I was trying to convey in that slightly difficult sentence. The idea is that when you induce a current, when you induce a magnetic field and a current in something, the direction of that current and that field will be created in a direction to oppose the change that created it. So when the south approaches, this becomes a south to oppose the south creating it. In the converse example, when the south is moving away, this becomes a north again, because that opposes the change that created it. South is retreating. The way to undo that is for the north to attempt to attract it back. And so the direction is created in such a way that it opposes the change that created it. I hope that's clear, and I hope I've gone over it enough for it to be clear. Let me just adjust my camera. And I'll learn from my mistakes this time. I'm going to turn the light off before I attempt to stand in front of it. And that's what you're seeing there. I've misnamed it here. It still says Fleming's left-hand rule on there. Please ignore that. This is not Fleming's left-hand rule. As I said, if you do A-level physics, you'll come to know it as Lenz's Law, L-E-N-Z, Lenz's Law. But it's this idea that the induced magnetism is induced in a direction to oppose the change that created it. Well, I'd like you to try a little bit of work now. So I must have put my PowerPoint clicker down somewhere. There it is. And you have the questions that I'm talking about. They are quite in-depth. I'm just looking at the time. As always, we're going to overrun a little bit, but perhaps only by 10 minutes more than the lesson would normally be. I will give you about 12 minutes. I think these questions have a little more to them, and 12 minutes even might not be quite the right timeline. So if it's coming up to those, and I'll give you warnings, just at least one or two of you, if you just say more time, please, I'll respect that and I'll give you more time. So I'm going to give you an initial 12 minutes. If that's nowhere like the right time limit, then I want at least one or two of you as we approach that 12 minutes to say more time, please. And what I'll probably give you is 5 minutes more. For now, though, we will do 12 minutes. So I hope these questions are understandable to you. Give them your best shot, and we'll go through them, and that's the lesson. Off you go. You've had just over half your time. There's 5 minutes left. I will, on about the 2-minute mark, put out that question about if people need more time. So you don't need to respond to that yet, just keep working. But in another 3 minutes time, I'll see if you're going to need longer. Just carry on for now. We've just passed that 2-minute mark. So yeah, don't feel like you're only speaking for yourself. You won't be. Do you need more than 2 minutes? Just reply with more time if you need to have more time than you have. Harry, I didn't find out how a brushless motor works. I will do for tomorrow. I'd forgotten all about that. That's, yes, I will do. Thank you for the reminder. Well, I didn't hear anything that suggested you needed more time. Don't worry if you haven't quite finished. It's certainly not the end of the world. But actually, you'll see you don't have to write much to write good physics, and that's certainly the case here. That actually you can pick up a lot of your 6 marks just by using some of the words that I've taught you. There is one phrase that might have eluded you all. We'll see, but we'll go through them now, and you can see how you did. Just moving the camera once again. Right. So you have this in front of you. Nevertheless, I'll read through it just to remind you of the context of this first question. It said, the figure below shows a coil and a magnet. An ammeter is connected to the coil. So over on this coil, we have a complete circuit. We're not given the poles of the magnet. Clearly, that doesn't matter for this question. It's asking for general principles. And the question continues. The ammeter has a center zero scale, like the one you saw me demonstrate with, where zero is in the middle. A center zero scale, so that values of current going in either direction through the coil can be measured. And question A starts like this. The teacher moves the magnet slowly towards the coil. Explain why there's a reading on the ammeter. Well, let's go through some of the things we said about the generator effect. Sorry, that noise was Dreamsky, typical of him. Let's go through some of the things we said. So the question has set up this idea that that is moving slowly in that direction. And so when it does, the first thing we can say is that the coil experiences a changing magnetic field. So I'm going to do this in note form as I always do, but coil experiences changing field. That's 1 mark, I would venture. Because it's part of a closed circuit, this is the next thing we're going to get across. That means that not only do we have a voltage, but we also have a current. Not only do we have a potential difference, we also have a current flowing. Let's use the best words we can here. So this induces a PD, standing for potential difference. A PD across the coil. Now, there is a phrase that examiners, or certainly exam mark schemes that I've seen, favour, and I know that we're not in a zone now where that matters, not for GCSE, but there'll be a phrase that if you go on to do A-level will be useful. We sometimes describe how the coil cuts through the lines of field. In other words, we can imagine that this magnet has a magnetic field around it. And I'm making a mess of my page. And because this is now moving, these lines of field cut through the coil, or vice versa. The coil cuts through the lines of field. I'm going to drop that in here. So this induces, sorry, a PD across the coil. And then I'm going to add because coil cuts through. Cuts through is just a really useful phrase here. Now, none of you will have written that, I don't think, because I didn't teach you to. But yeah, the coil cuts through the magnetic field. But let's now take this idea of a potential difference forward. Because there's a complete circuit, so I'm going to put because circuit complete. That's what means a current flows. Because circuit complete, current flows. And that is why there's an ammeter reading. The question had asked to explain why there's an ammeter reading, so I'll just put hence ammeter shows reading. So I think you'll have scored high. You'll have potentially got 5 out of the 6 because I think this thing is just not something I equipped you for. But hopefully you got the idea that the coil experiences a changing magnetic field, not necessarily in those words. The idea that a potential difference is induced. There's a chance you skipped that step and went straight to current, in which case you probably lost a mark, maybe. That potential difference was induced because the coil was cutting through the lines of the magnetic field. And then because the circuit's complete, a current flows. And because a current flows, the ammeter shows a reading. I hope it's clear-ish. Any questions you can ask, but I hope it's clear how you get the marks there. Right, yeah. So I've just become aware of a connection issue, but I think it's fixed now. Sorry about that. Part B. The table below shows some of the other actions taken by the teacher. Complete the table to show the effect of each action on the ammeter reading. So in the first one, they keep the magnet still and they move the coil instead. Well, there'll be some sort of small reading or small deflection. Anything that shows that there will still be a reading on the ammeter gets the mark there. In the next one, they hold the magnet stationary within the coil. So actually nothing is moving there. And whenever there isn't anything moving, there's no reading. You only get the generator effect when there is a changing magnetic field. So there'll be no reading if both things are still. In the next one, they move the magnet quickly towards the coil. And there'll be a larger deflection than before, or a larger reading. And then they do the same thing, but they reverse the magnet and move it slowly towards the coil again. So it's going to be a small deflection again, but we need to deflection. But the thing that really gets you the mark is this: in opposite direction. I'm just saying DIR for direction. A small deflection, the opposite direction. Right. Part C, last part of this question said, the magnet moves so that there's a steady reading of 0.05 amps on the ammeter for 6 seconds. Calculate the charge that flows through the coil during those 6 seconds and give the unit. Well, I'm wondering how many of you remembered this without having to look back. Well done if you did. Charge flow equals current times time. Q equals IT. Putting the numbers where we know them, there's no conversion needed. We have a current of 0.05 times by 6. And you run that through a calculator if you need to. So 0.05 times by 6 is 0.3. Should have been able to do that in my head, thinking about it. 0.3. Well, this question has a whole extra mark for the unit, and charge flow is measured in coulombs. Really well done if you remembered every part of that, because that is digging deep in the memory bank. That's out of 13. I should have said that. So 6, 4, and 3 adds up to 13. You can give yourself a mark out of 13 if you want to track such things. We'll go on to question 2, and that will be our lesson done. Thank you for bearing with me through these when they take a little longer. So question 2 puts all these ideas into some new context. P waves and S waves are 2 types of seismic wave caused by earthquakes. Which one of the statements about P waves and S waves is correct? Well, it's not the first one. P waves and S waves are not transverse. It's not the second one. P waves and S waves are not both longitudinal. So it's about getting right the way round of the last 2. And it's the last one, is that P waves are longitudinal, primary waves are longitudinal, and secondary waves are transverse when an earthquake happens. Next question. Seismometers on the Earth's surface record the vibrations caused by seismic waves. Figure 1 shows the vibration recorded by a seismometer for one P wave. Question B asks this, calculate the frequency of the P wave shown in figure 1. What I will say is, you'd normally have had a data sheet that would have made this question easier if you struggled. It would have directed you towards the data sheet and a certain equation contained within. You've got to do a couple of things to get this, and I think it's very harsh that it is only worth 1 mark. You can do it through an equation, you can do it through your understanding of what frequency is. But first, we have to identify how many waves are in this picture. Well, that's 1 complete cycle. That's a 2nd complete cycle. That's a 3rd complete cycle. And that's a 4th complete cycle. There are 4 waves on that picture. Once you've identified that, we can use some of the information we're given. So we're going to assume that each wave is the same width. We're not told that, but I think we can be given to assume that. And so if 4 waves is 10 seconds, then we can know that one wave is equal to 2.5. What I've done there is I've taken the 10 and I've divided it by the 4. And when I say one wave's equal to 2.5 seconds, that's loose wording. What I mean is that t, the time period of that wave, the time period of that wave is 2.5 seconds. And the equation I was talking about before that allows us to calculate frequency is this, f equals 1 over t. As soon as you know the time period, you just work out its reciprocal. So we need to do 1 divided by 2.5. I'm just doing that on my calculator off screen. But I'll show you the working here as well. So to find the frequency, it's 1 divided by 2.5, which in this case is 0.4. Our frequency of this wave, 0.4. You might have gone straight from the fact that there are 4 waves in 10 seconds and just divided it by 10. That would be another way of doing it. Because if you knew the definition of frequency is the number of waves per second, then you can just divide by 10 to get 4 waves divided by 10. 0.4. Question C. Write down the equation that links frequency, wavelength, and wave speed. It does not have to be in that order. I'm not going to use it in that order. I'm going to do wave speed, V, equals frequency times wavelength. V equals F lambda, or wave speed equals frequency times wavelength. Question D. Leads on from there, because it asks us to do a calculation. The P wave shown in figure 1 is traveling at 7,200 meters per second. Calculate the wavelength of the P wave. Well, let's write out the wave speed equation, and let's put the numbers where we know them. We know the speed, so V becomes 7,200. That equals the frequency we worked out before, which was 0.4, times by lambda, the wavelength. That's what we're trying to find out. So to find lambda, it's going to be 7,200 divided by 0.4. And again, you run that through the calculator, 7,200 divided by 0.4, and you get 18,000. So the wavelength of this is 18,000 meters. You could have added K for kilometers and just done 18 kilometers, but keeping it in meters absolutely fine because we were provided with meters. Question E, explain why the study of seismic waves provides evidence for the structure of the Earth's core. Well, again, this was digging in your memory, this time from only a month or 2 ago, but that seems like quite a long time at this stage. The fact is this, S waves cannot travel through liquid. Now this was only worth 2 marks. There's loads you could say there. So you could go into the detail of saying that when these waves move through Earth, that means there's an S wave shadow on the other side of the Earth. And that would all be great to put. But if I'm going to pick out 2 things that are the most important here, that's the first one. And then the second thing to get across is the outcome of all of that. this idea that this fact above, this has shown that Earth has a liquid outer core. I suspect some of you on that one will have written some great physics that doesn't get credit here, and that's not bad question answering, that's bad luck. But I think the 2 marks to get across here are the fact about seismic waves and what we can conclude from it. If you, as I say, have talked about how there's S-wave shadows on the other side of the world, and so we've inferred the structure from there, that is all great physics to describe. But in this case, I think start of the process and end of it is probably the best way to answer it. And then we're nearly there. And a simple but ingenious invention now that we know about the generator effect is this. Figure 2 shows a simple seismometer made by a student. So you can see how it would work. If there were an earthquake, this whole thing would start wobbling on the spring and it would induce an electrical current in this coil. It's a really clever idea. To test that the seismometer works, the student pushes the bar magnet into the coil and then releases the bar magnet. So you can imagine this bar magnet will be wobbling up and down for some time. And we're asked, why does the movement of the bar magnet produce a potential difference across the coil? And this is only worth 1 mark, and yet it's a very similar question to question 1 that was worth 6. But I think the key is this idea that it either cuts through lines of field. So either coil cuts through field lines, or, and I think this is what I'd have gone for in your position, something about how the coil experiences a changing magnetic field. Coil experiences changing M field, short for magnetic field. And then finally, question G. Why is the induced potential difference across the coil alternating? What that means, of course, is that, yes, one moment you'd have plus there and minus there, and then the next moment you'd have minus there and plus there. It is an alternating potential difference. The reason for that is simply that the magnet is changing direction. So why is the induced potential difference across the coil alternating? Because magnet is changing direction. Now, of course, you're not going to have put my words, but anything that gets that across is correct here. The idea that the magnet is changing direction. Well, that's those gone through. So let me just get you back on, let me get myself back on the screen for me to just say some goodbyes and some further instructions. So once again to you, oh, it's bright, but I'm going to put up with it because we're at the end now. Thank you to you, Loyal 10. Really, really lovely that you're doing this, and I hope that it's providing something different, because all of our lives could be a bit monotonous at the moment. Tomorrow is Good Friday. It's a bank holiday, not that that really makes much difference these days, but it is a day of religious observance. It's a day where I myself, or if you can't make it, I'd absolutely understand if you're doing things with your family. It's just a different day, isn't it? So by all means, you can just watch this afterwards. You don't have to watch it at the scheduled time. But it is nice when you all get together and I can see all 10 of you all watching at the same time. There's something nice about the sort of collaboration there. So if you can make it, more the better. Because I'm a creature of habit, I'm going to do it when we would have had lesson 4. So that's 12:25, and I'll be online from 12:15 for you to sign in. And we're going to take this generator effect forward. I'm going to show you how you make the sort of generators that work in power stations, things called alternators, and how you make something called a dynamo. What I don't have is much of the equipment to physically make them, but I will show you possibly 1 or 2 bits of demonstration there. But tomorrow we learn about how alternators and dynamos work using this generator effect. So for now, just look for your emails. I'm about to send you an email with instructions and things to print out. There's, I think, 2 or 3 things to print out for tomorrow. Stay safe. I hope you're all okay, and I hope all your families are okay. And I will see you again tomorrow. So bye for now.